So in my previous recording, I was in this slide, and then suddenly it stopped because there was some problem with my the storage of my computer. So I'm really sorry for that. I'll just go back. So because I was continuing the teaching, I was continuing the derivation, but somehow abruptly it stopped. I did not notice. So I'll just go back a little bit, and I'll just tell you. So this is the slide where it stopped. So as you have seen that based on R alpha, which is basically the site occupancy or fraction of alpha sites that are containing A atoms, or the right mounted atoms is R alpha. So you know the definition of R alpha, and you know the definition of R beta, right? So I will just reprise quickly. So if you know the definition of R alpha and R beta, so you know basically R alpha and you know R beta, and then you also know XA is the mole fraction of A, and XB is the mole fraction of B, and we have taken an alloy composition of XA equals to 1 by 2 and XB equals to 1 by 2, right? And we told that R alpha is the fraction of alpha sites occupied by A. And R beta is the fraction of beta sites occupied by Also we defined L, which is the long range of the parameter, as R alpha minus XA by 1 minus XA, which is equals to R beta minus XB by 1 minus XB. Now when R alpha equal to 1, then you have and equal to R beta, right? R beta or R alpha 1, and basically if L equal to 1, right, which is complete is also in, right? And we also know if R alpha equal to XA, or R alpha equals to XA, or R beta equals to XB, right, then in such a case you get L equal to C. That is complete, right? That XA or XB, as you remember, that it is basically coming as a random alloy approximation, right, that we use in regular solution model, right? Finding the probability of finding an A atom on the lattice site is equals to XA is a regular solution assumption or a random alloy assumption, right, or random alloy approximation. So basically if we put R alpha equal to XA or R beta equals to XB, we basically get a long range order parameter of 0, which basically tells complete disorder, right? However, we also started with a 50 atomic percent A, 50 atomic percent B, which corresponds to a NIL type lattice or a B2 lattice, right? It's a B2 lattice. One common B2 lattice example is NiAl, right? NiAl has a B2 structure. Nickel aluminide has a B2 structure. So basically, if you look at that, you have 50% nickel, 50% aluminium, or 50% A and 50% B. Now, if that is so, I can write L equals to R alpha minus half by 1 minus half, and from there we could do like 2L, right? 2L. 1 minus half is basically, let me write this one. So 1 minus half is half. So basically what we get is 2 R alpha minus 1 equal to L, or R alpha equals to 1 plus L, right? So we basically got R alpha equals to 1 plus L. Similarly, for XB, if I do the same way, R beta is 1 plus L by 2. Now we get W alpha, which is basically 1 minus R alpha, that is the fraction of alpha sites occupied by the wrong atoms, that is the B atoms, which is basically 1 minus 1 plus L by 2, which is basically 1 minus L by 2. And W beta is equals to 1 minus R beta, which will be again be 1 minus L by 2. Right? Now we have N by 2 or 50% alpha sites. If you have total number of sites is N, total number of lattice sites, and N by 2 is alpha sites, and N by 2 beta sites. So basically what we are now telling, what is N by 2? So basically if I tell R alpha times N by 2, what does that mean? This is number of A atoms in alpha, right? R alpha times N by 2, and R alpha is nothing but 1 plus L by 2, 1 plus L by 2 into, which comes out to be 1 plus L by 2. Similarly, we have written number of A atoms on alpha site is 1 plus L by 4 into N. Similarly, we can write R W alpha into N by 2 is number of B atoms on alpha in alpha site, or in alpha sites. So if I look at that, which is basically 1 minus R alpha, 1 minus R alpha is basically 1 minus L by 2. So basically this will become equal to 1 minus L by 4. This is 1 minus L by 4. So basically this is where we start here again. So this is 1 plus L by 4 into N, which is number of A atoms on alpha site. Number of A atoms on beta site will be 1 minus L by 4 into N. Similarly, number of B atoms on beta site is 1 plus L by 4 into N, and number of B atoms on alpha site is 1 minus L by 4 into N. Now you see, if I want to know the number of AA bonds and number of BB bonds and number of AB bonds, what do I do? First I find the probability of finding an A on an alpha site, which is basically given by R alpha. Now probability of finding an A on beta site is given by 1 minus R beta or W beta. So basically, if Z is the coordination number of sites, basically what we are talking about is like, if I am at an alpha site, what is the coordination number that we, or the nearest coordination, so what are the nearest sites that we can go to? So basically if you look at that, you will basically, if you look at the BCC, where the B2 ordered lattice, then each alpha site, which is the body center, right? This alpha site is nothing but so we have depicted this as body center. You can also do it for a corner, you just have to draw some extra unit cells, right? So if you look at one body center, if you look at the body center, alpha site, if it is at body center, then it is surrounded by Z times beta sites, where Z is the coordination number. So B2 again, remember, is a BCC derivative. So Z is going to be 8, right? So you can actually see that. So if you look at the picture that we drew, right, you have the alpha site, which is the body center, which is surrounded by 8 corners, right, which is the beta. These 8 corners are the 8 beta sites. So it is basically Z beta is nothing but 8 beta when it comes to B2 units. If you have a B2 structure, then the B2 unit cell, you have 8 beta sites that are surrounding one alpha site, right? Now if that is so, you have the A, probability of finding an AA pair is basically Z, right? It's basically Z times R alpha, right? R alpha is probability of finding, so R alpha is basically A on alpha site, right? So basically A on alpha site, and 1 minus R beta is A on beta site, right? 1 minus R beta is A on beta site. So this is A on alpha and this is A on beta, and so basically that gives me AA pair. So this is Z R alpha 1 minus R beta. So basically R alpha is 1 plus L by 2 and R1 minus R beta is 1 minus L by 2. So this becomes 1 plus L into 1 minus L by 4 and there is a Z. Right, so this becomes Z into 1 minus L square by 4. Now if I know the probability of finding one AA pair, now I can estimate number of AA bonds. Only thing, always remember, if I am at an A and I am counting another A, so this is at an alpha side, this is at a beta side. Now from when I am in the beta side, then I am also again counting the A on the alpha side. Right, so basically there is a double counting, so therefore we multiply. When I look at NAA, we have PAA times N. Instead of writing PAA times N, I will write PAA times N by 2 because there is a double counting. So you have one terminus to the other terminus. So if you have here the alpha side and here beta side, you can come to beta side and count this alpha side again. So there is a double counting. So there is a 2 here. Now that actually gives me more simplification because 2 times 4 is 8 and Z is also 8, right, for B2. Since Z is 8 for B2, I can write this NAA, that is number of A bonds is basically, right, number of A bonds is basically 1 minus L square, right, 1 minus L square into N because Z is 8, 4 times 2 is 8, 8 and 8 cancels out, so this becomes 1 minus L square, right. Similarly, for NBB, it will be equal to Z. So if I look at NBB, it will be Z R beta 1 minus R alpha, that is equals to PBB. Right, now this PBB times N by 2, so PBB times N by 2, again this double counting will come. So as a result, so if that is so, then you have R beta which is 1 plus L by 2 and 1 minus R alpha which is 1 minus L by 2. So basically you get NBB to be exactly the same as NAA. There is number of BB atoms and that is the number of BB bonds and number of AA bonds have the same expression. NAA has 1 minus L square by N, NBB also is 1 minus L square by N. Right, now comes NAB. Now for NAB, look at this. So if you have R alpha, so probability of P A on alpha and B on beta, or you can think of this is basically Z equal to Z R alpha R beta. Now P A on, so you can write B on alpha. Say for example I am on B on alpha. If B is on alpha, I have to have A on beta, right, for an AB bond. So this basically becomes Z W alpha W beta. Right, so B on alpha is W alpha and A on beta is W beta. Right, so W alpha, W beta, which is 1 minus R alpha, 1 minus R beta, right, which is 1 minus R alpha into 1 minus R beta. Right, so basically you have that. So you have Z, again you have this Z coordination number, right, which is for B2 it is 8. So R alpha R beta, 1 minus R alpha, 1 minus R beta. Now again you can see that you are going from A and alpha or A on beta. See, you are looking at A on beta, say for example, with a B on alpha, or you are looking at A on alpha and B on beta. Now if you are looking at that, you have AB as well as BA, so there is a N by 2, right? There is a double counting, right? There is a double counting. So if it is so, you have this N by 2 here, or if you have N by 2 here, and R alpha times R beta is 1 plus L square by 4, this is 1 minus L square by 4, and this is N by 2, and there is a Z here. So basically if you see 2 times 4 is 8, 8 and Z cancels out, so you have 1 plus L, 1 plus, so this is basically going to be 1 plus 2L plus L square plus 1 minus 2L plus L square. So 2L minus 2L plus 2 goes out. So you get 2 into 1. So basically you get what is equal to, right. So basically I will do one thing. This is the rough work that I have done, right. And so if you see that this comes, so there is this N by 2 factor, right. So this is N by 2 factor, because why N by 2? Because it cannot be n simply, because if it is n simply, then you are doing a double count, right? So it's n by 2, so 2 4 is 8, and there is 8, so basically this, and so this 1 plus L whole square plus 1 minus L whole square basically becomes 1 plus L square, but there is a 2, right? Because 1 plus L square, and again here is 1 plus L square, which is 2 plus 2 L square, which is 2 into 1 plus L square times n. Now if you look at that, the enthalpy of mixing is nothing but NAA, right? It is NAA EAA plus NBB EBB plus NAB EAB, right? We are only looking at the nearest neighbors. Now if it is so, NAA and NBB has the same expression. So basically NAA and NBB have the same expression, which is n into 1 minus L square, right? So basically that's what it is, right? You have NAA or NBB, which is 1 minus L square into n. So 1 minus L square into n is taken common, and you have EAA plus EBB. EAA and EBB are the bond energies, right? AA bond energies and BB bond energies. Remember that A can be, so here when I am looking at AA on this ordered lattice, it is like A on an alpha side and A on the beta side, right? So now for EAB, which is 2n 1 plus L square, just we have put 2n 1 plus L square, so that's what I am doing, 2n L plus L square into EAB. Now you have, that is the NAB EAB. Now if you have that, you already got what is called the enthalpy of mixing for the ordered lattice, right? For the ordered lattice. Now you will use Boltzmann's law, S conf equal to Kn omega, to basically, or Kn and W, to get the configurational entropy, right? So W equals to, now if you look at that, the first part is for the alpha sides, right? First part. Now I'll do one thing. The first part, if you look at, is for the alpha sides, right? This is alpha sublattice. In fact, it is called the alpha sublattice. So, and then there is a multiplication. And again, if you look at this, this is for the, so this is for the, so the top one is for, so top one is alpha sublattice. So in alpha sublattice, okay, you have n by 2 sides. Now in n by 2 sides, you are arranging, okay, in the n by 2 sides, that n by 2 alpha sublattice sides, you are arranging A and B. So you have number of A atoms on alpha factorial, and so in the denominator you have number of A atoms on alpha factorial, A on alpha factorial and B on beta alpha factorial, right? A on alpha factorial and B on alpha factorial. So if you think of that, A on alpha we have already written, right? We have already written, A on alpha is 1 plus L by 4 into n, and B on alpha is 1 minus L by 4 into n. So basically that is what we are writing with the factorial. Now this is for the beta sublattice. This term is for the beta sublattice. Remember, it's a product of two, a product of arrangement in the alpha sublattice and beta sublattice, because the entire ordered crystal is made of two sublattices. One is alpha, another is beta. So this is for the beta sublattice. This is for the beta sublattice. Now if that is so, again for beta sublattice, it's 50-50, right? Alpha, number of alpha sides are 50% and number of beta sides are 50%. It's basically n by 2 and n by 2. So you have n by 2 factorial in the numerator in both, and you have only in the denominator you have the A atoms on alpha factorial, means how to arrange A. So basically you are arranging this n by 2 atoms on this n by 2 sides, on this n by 2 alpha sides. And how are you arranging? You are arranging A atoms and B atoms, and as you know that number of A atoms on alpha, they are basically indistinguishable between one another, and again number of B atoms, so basically the A atoms are indistinguishable, right? They cannot, you can distinguish A from B, but A from A would not. So basically you have to write this formula, right? We wrote previously n factorial by NA factorial and B factorial, for example, for regular solution model, right? So you have now, because NA factorial, why? Because NA was the number of A atoms and NB was the number of B atoms. Now in this case, we are looking at number of A atoms but on alpha, so which is 1 plus L by 4 into n, and this is 1 minus, so this is basically, this is going to be 1 plus L by 4 into n, and this is 1 minus L by 4 into n. By the way, you will see that for the beta sublattice also, this is exactly the same. This is 1 minus L by 4 into n, and this is 1 plus L by 4 into n, right? And these are factorials. So if you look at that, you have ln W, right? A6k ln W. So we found out W. Now if you I am looking at k. K is the Boltzmann's constant. So k ln w or k b ln w. And if you look at that ln w, which is ln n by 2 factorial 1 plus l by 4 into n factorial, right? This term and this term. Again you have a product now n by 2 factorial by the same terms, like 1 plus l by 4 factorial into n factorial and 1 minus l by 4 into n factorial, right? Now if you have that, what you can do, you can basically now take ln n by 2 factorial minus ln 1 plus l by 4 into n factorial minus ln 1 minus l by 4 into n factorial. But you see, it is the same here as well as here. So this becomes, so basically n by 2 factorial and again here n by 2 factorial. So this becomes 2n by 2 ln n by 2 factorial. This is 2 ln minus 2 ln 1 plus l by 4 into n factorial. It is minus 2 ln 1 minus l by 4 into n factorial. And if that is so, you can write now, further you can simplify. So for example, now you can use Stirling's approximation. What is Stirling's approximation? N factorial ln of n factorial equals to n ln minus n. Actually, there is also a plus 1, but that plus 1 is neglected because n is very large. So if that is so, you have 2 n by 2 ln n by 2 minus 2 n by 2, right? So basically, and here again 2 ln 2 1 by 1 plus l by 4 into n ln 1 plus n by 4 into n minus, so here there is a minus sign, so it should be plus. Now if you see this plus 2 1 plus l by 4 into n. Again here also there is a, so here also if you look at this guy, so again if you look at the Stirling approximation here, so you have 1 minus l by 4 into n ln 1 minus l by 4 into n minus, and this minus, and here there is a minus, so basically here there is a minus sign, here there is a minus sign, so I can put the minus sign properly, minus sign is here, so as you can see, and so you have 2 ln 1 minus l by 4 in factorial, so basically minus 2 this thing, but there is a n ln n minus n, right? So minus n means it becomes plus, so plus 2 1 minus l by 4 into n. Now if you look at that, 2 1 plus l by 4 into n, this term, basically this term, what is that? This term, right? 2 into ln n by 2 factorial is 2n by 2 ln n by 2 minus 2n by 2. So this term and this term and this term, if you combine, you get basically n here, and here you basically get 1 plus l by 2 into n, and here you get 1 minus l by 2 into n. You add them up, so basically you get here n minus n by 2 minus minus n plus n by 2 plus n by 2. So basically this can cancel. So these and these cancel out. Now if you see, you can further simplify. You have this term, you have now this term. Now in this term you have ln this term plus into n. So if you think of log of AB, this is what I use, is log of A plus log of, right? Or ln of A plus ln of B if it is ln A. Now what I am doing now here is, so you have 2n by 2 ln n by 2, right? So basically I am writing as n ln n by 2 minus 1 by n 1 plus l by 2 into n ln 1 plus l by 4 into n, and again, so basically I have just rewritten that for clarity, right? Because these terms have gone, right? This term and this term have become 0, right? They have cancelled out. Now if that is so, now if I write this guy I am writing as n ln n minus ln n 2, right? And here also minus 1 plus l by 2 n. Now this I am writing as a product, right? Log of a b equals to log a plus log b. So ln 1 plus l by 4, and then again you have the same minus 1 plus l by 2 into n. So this is exactly what I am writing here. So minus 1 plus l by 2 into n ln n, right? There is an ln n. Similarly, if I expand here also 1 minus l by 2 into n ln n, and then again minus 1 minus l by 2 into n ln 1 minus l by 4, right? So now you have this term, right? This has ln n, this has ln n. There should be another term. Yeah, there is one more term with ln n. So you have ln n, you have now n as common, minus 1 plus l by 2 into n, minus 1 minus l by 2 into n. So if you look at that, this becomes basically n minus. So if we have, so if this is 1 plus L and this is 1 minus L and there is by 2, so it is minus n by 2 minus n by 2 and this is plus n, so this becomes 0, right? This term becomes 0. Now you have minus n, and now if you simplify further, you have ln2, and if you are having like 1 plus L by 2 and n you can take as common, right? You can take n as common now, right? You can take n as common now here and here and here, right? So if you take that as common, I have taken that, I have taken minus n as common in fact. So I have ln2, but since minus n I have taken as common, minus n, so this becomes plus ln2, right? So minus n is common, so this is ln2, and if I now look at n again here, so now you have minus I have taken as common, so this becomes plus, right? So basically it becomes 1 plus L by 2 ln 1 plus L by 4 and 1 minus L by 2 ln 1 minus L by 4. Now you have minus n common, ln 2, and this is 1 plus L by 2 ln 1 plus L, right? ln 1 plus L, and this is again, this is like ln a by b equals to ln a minus ln b. Exactly, that's what I am using. So ln 1 plus L by 4 I am writing as ln 1 plus L minus ln 4, and you have also this coefficient which is 1 plus L by 2, right? 1 plus L by 2. Similarly, for this term you have 1 minus L by 2 as coefficient, and this is written as ln 1 minus L minus ln 4. Now if you see, so you have a minus sign ln 4, here also minus sign 4, right? So basically if I take this common, because ln 4 is nothing but 2 ln 2, right? 2 ln 2, because ln 2 square is 2 ln 2. So you have ln 2 minus 1 plus L ln 2, right? You have ln minus 1 plus L ln 2, because 2 and 2 cancels out, right? If I put out 2 here and I have 2 ln 2 and 2 and 2 cancels. So you have 1 plus L ln 2 minus 1 minus L ln 2 and then plus half, right? There is a half remaining. 1 plus L ln 1 plus L plus 1 minus L ln 1 minus L. And basically if you now rearrange, you get ln 2. Now if you see, here there is a minus sign, there is ln 2 here, and see if you look at this, if you add them up, 1 plus L and 1 minus L, L cancels out, so this becomes ln 2 minus 2 ln 2, which is minus ln 2, and there is a minus sign, absorb the minus sign, so this becomes ln 2, and this guy becomes plus, becomes minus, right? So ln 2 minus half, 1 plus L, ln 1 plus L, plus 1 minus L, and 1 minus L, and if you see n, if I assume n number of lattice sites, n is basically equal to Avogadro number for 1 mole of atoms, right? 1 mole of the material or 1 mole of the ordered phase. For 1 mole of the ordered phase, n is nothing but the Avogadro number, and then R is the universal gas constant, is equal to Boltzmann's constant times n, and so if you get this, you get the configuration entropy as R ln 2 minus half 1 plus L ln 1 plus L and 1 minus L ln 1 minus L. So S-conf is a function of the long range order parameter. And now if it is so, if I put L equal to 0, I get S-conf equal to R equal to 2. Remember, regular solution, S-conf is R equal to 2, right? If it is a 50-50 solution, you have minus R xi ln xi, right? Minus R, and I is repeated, so it's summed over. So you have I equal to 1 to 2. So you basically have, and now if I tell x1 equals to x2 equals to 0.5, then you basically have minus R half ln half plus half ln half. So basically ln half, so minus R ln 1 minus ln 2, which is basically ln 1 is 0, so which is basically R, right? The other term cancels out when L equal to 0. Why? Because if I put L equal to 0, this is 1 and this is ln 1, and L equal to 0, this is also ln 1. So ln 1 is 0. So this term vanishes, right? And so you only get R ln 2, which is exactly for the disordered value, right? If it is a disordered solution or disordered liquid solution, I get the same R ln 2. However, in the limit of L equal to 1, if you look at that, this is ln 2, this is half minus half, and this is 2 ln 2, right? L equal to 1. So minus half into 2 ln2 is basically minus ln2. So ln2 minus ln2, but there is one more term. Now in this term what happens? If I put L equal to 1, then 1 minus 1 is 0, but I cannot really do that directly. That's why in the limit, that's why we write in the limit of, because if I don't use in the limit of, if I put L equal to 1 directly, then 1 minus L is 0 and log 0 is undefined or ln 0 is undefined. As a result, it is important to tell that when I put L equal to 1, in the limit of L equal to 1, like L is going as close to 1 as possible. So then 1 minus L is supposed to be 0 and ln 1 minus L is supposed to be basically the ln 1 minus L is supposed to even be finite, but it is multiplied by 0. So this is 0 and this is minus ln2, this is plus ln2. So basically when in the limit of L equal to 1, the configurational entropy vanishes, right? If it's complete order, there is no configurational entropy, but there should be something else, right? And that part we can basically use something called vibrational entropy. Now if you have that, you have H, right? You have the order. For the order lattice, you have the enthalpy of mixing or molar enthalpy of mixing, and you have now the molar entropy of mixing, right? Molar entropy R is there, so it's molar entropy of mixing. And G, which is basically molar free energy of the ordered phase, is H minus Ts, which I am now writing as H. We already know H is nothing but the H order, and S is nothing but, so now S is basically configurational plus vibrational. I can include vibrational entropy also, but if you see, H order has n1 minus n square, Ea plus EBB plus 2n. So basically there is no S. Is 1 plus n square EAB, and then RTLN2. So T temperature dependence is there, right? You get the temperature dependence. So by that, if you do the second derivative of G and put it to 0, you basically get the TC. Okay, you can try that. You can find the TC. I'll discuss it in week 11 about stability. So basically now you have G equals to these terms, which is the interaction term, this part. And then this term, which is basically the configurational entropy part, is RTLN2 minus half 1 plus ln 1 plus L plus 1 minus ln 1 minus L. But you have also an additional term which you can use, which is like n times SV0, where SV0 is the vibrational entropy per atom, right? And n is the number of atoms, so it is vibrational entropy per atom. And if you have 3 n independent oscillations using the statistical mechanical concepts that have been taught in the statistical thermodynamics classes, you can basically arrive at, so I am not going to do the entire derivation here, but I am just writing it. So you will come out with this 3n, if you assume 3n independent oscillations, then the vibrational entropy comes out to be kb, and all this beta epsilon y, where beta is 1 by kbt, right? So beta is basically 1 by kbt. So if you look at that, you have this e to the power beta epsilon y, and epsilon I are basically the energy levels, right? These are basically the 3n energy levels that you have, right? I equal to 1 to 3n. So you have 3n oscillations, that means there are 3n energy levels, right? If you have 3n oscillations, so you have h nu I, so epsilon I equals to h nu I, right? Nu I is the frequency, nu is the frequency. Now this is something that I want to give, and this will be merged with the earlier lecture. So basically it becomes a continuous lecture. You have to just listen to it in a merged form, and then in the next lecture I will basically discuss the phase equilibrium in multi-phase, multi-component, non-reacting systems. Basically, I look at now the same concept that I have taught before of phase equilibrium across subsystems, right? Phase equilibrium across subsystems. Now, the subsystems are nothing but, in this case, phases, right? Across subsystems, and also I look at something like called phase diagram, right? Or phase stability map. So, phase diagram or phase stability map, right? This is something that I will do. Okay, so in the just wait for the next lecture. So in the next lecture, I will basically discuss all these different phase equilibria, the interesting phase equilibria that you can see in multi-phase, multi-component, and non-reacting. So basically, although I am talking about multi-component, most of the discussion that I will do here is basically focused on binary alloys. But yeah, you can also look at ternary alloys or ternary systems. It need not be alloys, it may be ternary oxides or ternary carbides, right? Or you can go beyond ternary. But remember, when it comes to phase diagram, if you go beyond ternary, it becomes very difficult to visualize, because even in tunnel, you require basically a 3D model. Now we can take sections of a 3D model. Again, if you go beyond tunnel, again you have to start with taking sections, right? That is something that you have to do, and I'll discuss that in the next lecture.